Hey everybody, this is Mrs. Hilt, and in this lecture we are going to go through slides 8 until the end of Notes 11, Introduction to Acids and Bases. Now, if you did not hear the first 7 slides or were taking a test or absent yesterday when we went through those, please pause the video or read through those first 7 slides. And the one slide that you'll probably need the most help on is number 7. I have a video linked in the weekly agenda and assignments document, as well as in topic folder number 11 that is linked with these set of notes that go over the answers. It's a different teacher, but she does a great job explaining the answers to these. For everyone else, we are going to quickly review our definition of acids and bases and then continue on. So, review. Bronson-Lowry theory. This is the theory or definition of acids and bases that we will be using because it is very general and versatile. So acids are proton donors, and we can see that in this example because we have HCl that ends up forming a negative ion or chloride ion. Therefore, its hydrogen was donated. We can see right where it was donated. It was donated to the water to form a hydronium ion. And whenever you see a hydronium ion in the products, that is an indication that this solution is acidic. For bases, these are proton acceptors. If we have a proton donor, we need somewhere for that proton to go, and it goes to the base. We have NH3, that is the base because on the other side of the equation, you can see that it forms NH4, and it is positive. So it accepted a proton, it accepted a hydrogen ion. In this case, water is acting as an acid because it donated its proton. And because it donated its proton, it ended up forming a hydroxide ion. Okay? And whenever you see hydroxide ions in the products, that indicates that the solution is basic. All right, that was a quick review from yesterday. Now we're going to get into how we can actually quantify this and relate it to the pH scale. So how we're going to do this is by using the concentration of the H3O plus and OH minus to figure out what the pH is. Okay? And I'm wondering, like, where is that coming from? It's coming from right here. Okay, so if we know the concentration, so the molarity of this, we can figure out the pH. And if we have more H3O plus, that means it is acidic. If we have more OH minus, the solution is basic. If they are equal, then of course they are neutral. And the closer the two concentrations are to each other, the closer the pH is to 7. The further apart, the further away that the pH is, closer to 1 or closer to 14. And these brackets, remember, are just indicating concentration. So let's write down what I mean by that. Concentration is the molarity. We find by taking the moles over liters, so N over volume. All right, now we can use those concentrations and figure out what the pH is. We'll get into the calculations on the next slide. And some of this you guys might already know, but we'll review it just in case. Acidic solutions are solutions that have a pH less than 7. Neutral, equal to 7. Basic are going to be greater than 7, all the way up to 14. And for acids, all the way down to 0. And the range can go outside of 0 and 14, but those are just the most common ones. All right, I thought that was a nice fun picture, very colorful, and lots of examples on it. And when we are calculating pH, this is actually, or the pH scale is actually a logarithmic scale. So that log button, literally capital L-O-G on your calculator, we're going to start using that to figure out what the pH is, so one of these numerical values, based on the concentration. And every time that you increase on the pH scale, you are actually going up by a factor of 10 because the pH scale is logarithmic, right? So if you actually go up, this example, 2 spots, you went up, the concentration is 100 more in OH, or H3O plus ions. Kind of crazy. Or sorry, I went the other direction. It is 100 less going to 6, and 100 more going toward the 4. So that backward originally. So more H3O plus, 100 less H3O plus. Because this is more acidic, so that's why we have to have more H3O. All right, so how we're actually going to go about calculating this is right here. And this can look scary. Don't let it look scary. You use your calculator for most of it, and what you plug in here is a concentration, aka a molarity, right? So how are we going to find the pH of a solution that has a concentration of 1.0 times 10 to the negative fourth molar? We'll take the pH of that, or we'll find the pH by typing in the negative sign, hit the log button on our calculator, typing 1.0 times 10 to the negative fourth, close the bracket, press enter, and you will get 4. So the calculator does all of the crazy log stuff for us. All right, so that means that if we have a concentration, an H3O plus concentration, indicating an acidic solution, or indicating the quantity of H3O plus ions, if it is that quantity, we have a pH of 4. That is definitely an acid. All right, now there is also a pOH scale, and we aren't going to deal with this too much. We really only deal with the pH scale, but it's good to know about it because if you go on to a higher level of chemistry, you will definitely use this. And it is really just like the opposite because it is measuring the OH concentration. Okay? And solutions that have a high OH concentration have low pOH values and therefore have high pH values. And solutions with low OH concentrations have high pOH values and have low pHs. Okay. All right, we'll get into an example of that calculation. Let's see. All right, so if we wanted to figure out what the pOH of something was, we need to compare the pH and the OH to the full scale. All right. So in a solution with a pH of 3.5, we can calculate the pOH from the pH. We'll go about doing that. We have the pH. pOH is equal to total scale minus 3.5. I realize I messed up on my sig figs right there. And our pOH is equal to 10.5. And that should make sense. If we have a pH of an acidic solution, pOH would be closer, it'll be higher up. Now, how we go about calculating the OH plus concentration from pH, so going the opposite direction, is by taking the pH and putting it as the exponent, the negative exponent of 10. So if the pH of a solution was 3, it's an acidic solution, we'll take 1 times 10 to the negative third, so the 3 comes into play, and that is the concentration of that acidic solution. I want you guys to pause the video and I want you to try identifying if these are acidic, basic, or neutral solutions. And I wrote some hints up here at the top. And don't forget that you do need to use your calculator for these. If you have to calculate the if you are finding the pH to see if it is acidic or basic, you first need to find the pOH. and you'll have to plug it into this formula to figure out what the pH is, and then compare it to the pH scale. When you're ready for the answers, press play. All right, let's check your work. All right, so A and C and D were pretty simple ones. Because it just stated what the pH was, we could compare this to the pH scale and see that, well, A and C, below 7, both of those are acidic solutions. D, pH of 7, that is neutral. And I did not intend for these to just be the neutral colors. That's just what I ended up writing them as. Then, for the other ones, I used the logarithmic calculation to find pH. So I took the concentration that was given, typed negative log concentration into my calculator, and I got a pH of 8. So not super basic, but just it's over 7, so it's considered basic. There we go. And grab that one. Cool. Then the last two. For E, I was given the OH minus concentration. So this one involved a little bit more work. And the reason why I have this in red is because it ended up being acidic at the end. So I typed in the negative log, typed in the concentration, but because this was the OH minus concentration, what I calculated was the POH value. POH value cannot be compared to the pH scale, so we need to figure out what the actual pH is to compare it to that using that formula and a little bit of arithmetic. End up with a pH of 4.45, which is acidic. And the very last one, we have the H3O plus ion concentration. So plug that in, same way as we did it up here, but because it was the H3O plus, that means that we are calculating the pH, and it ended up at 11.3. All right, 2 slides left. This is just a list of strong acids and bases, and I know I talked about these ones a little yesterday, the ones that are in the halogen column, and then these ones that are in, excuse me, that are the alkali metals, just common strong bases, and we can notice a lot of similarities between them. See how all these strong bases have an OH presence? That is not a coincidence. OH many times indicates, or a hydroxide ion many times indicates that it is a base. That's why we have these OH minus concentrations compared to bases. For acids, many times they start with a hydrogen. Yikes, frog in my throat. All right, I will try to edit that out later. Sorry if I cannot. But you can't always rely on something that has an H coming first that is an acid. For example, H2O, water. Sometimes it's an acid, sometimes it's a base, but many times you can use that as a fallback. All right, last one. Now, if you are feeling confident, I want you guys to pause the video and try calculating these each out on your own. If you're not feeling confident, just wait and I will walk you through them. All right, so first one, what is the pH of a 0.15 molar solution of hydrochloric acid? So, hydrochloric acid, I know that this is an acid due to it being on that list of strong acids that was 2 slides ago now. And we've used this a few times as an example. This substance will donate that proton. So that means that this concentration is the H3O plus concentration. I'm going to copy and paste that right here. So how I find the pH is by plugging that concentration into that formula, negative log 0.15, and I got a pH of 0.824. And I did not have the correct sig figs. What am I doing? There we go. All right, then second one. What is the pH of a 0.52 molar solution of NaOH? So this was a strong base, also from 2 slides ago, and due to the presence of that hydroxide ion, which indicates a base, that means that we are going to have to calculate this just a little bit differently. We'll still start by taking the opposite log of the concentration, but because it's a base, we will be given the pOH. Again, I messed up on my sig figs. Oops. And once you have the pOH, then you can find the pH of it by using the pOH, or pH plus pOH is equal to 14. And we'll get a pH of, actually if we rounded that, I'm going to keep that there, round that, it would round up to 14 actually. All right. That is it for this lecture. If you guys have any questions, please let me know. Have a great rest of your day.